It is July 2nd, 2021, and today I will continue to talk about a high-speed optical non-volatile memory. It is a third part of 3 videos describing this memory. In this part I will talk about my measurements and experiments to realize the recording function of this memory. This picture shows the design of the memory. The memory consists of transparent L-gas waveguide which delivers the optical data path to the memory. A gallium arsenide PIN photodetector which absorbs the light and transforms the photonic data to spin data. An iron boron nanomagnet in which the data bit is stored. The recording mechanism of the memory is as follows. A circularly polarized light path excites spin polarized electrons in photodetector. Under applied voltage, the spin polarized electrons are injected into the nanomagnet and reverse its magnetization. In my first talk, I have explained details of my experiment which verifies the multiplexing speed of 2.2 terabit per second in this memory. The result can be considered as excellent. In the second talk, I explained my research on development of the reading scheme for the memory. 4 reading schemes have been proposed and experimentally verified. All schemes are efficient for reading magnetization data of nanomagnet. Even so, the 100% of required performance has not been achieved. The reading performance is reasonably good, and the present achievements in development of reading scheme can be evaluated as moderate. Today I will talk about the recording function. For this memory, the recording function means the mechanism of magnetization reversal of nanomagnet by spin polarized photoexcited electrons. At present, the recording function is most difficult to demonstrate experimentally, and several issues still have to be resolved. The first challenge is a high-speed injection. The spin lifetime is short, it is only about 100 picosecond in gallium arsenide. Within this time, the spin polarized photoelectron should be injected into the nanomagnet before the spin dies inside the gallium arsenide photodetector. The second challenge is the current injection from large size detector to very small nanomagnet. The photodetector cannot be infinitely small. The smallest possible size of photodetector is 4 by 4 micrometers. An optical pulse will not be absorbed efficiently in a smaller detector. In contrast, the nanomagnet should be as small as possible. The largest diameter of nanomagnet in which magnetization reversal is possible is about only 70 nanometers. The recording mechanism of magnetization reversal by injected spin polarized electron is well known, well studied, and already successfully used in commercial magnetic random access memory, or MRAM for short. This graph shows MRAM cell and mechanism of recording. Under applied voltage, the spin injection from the pin layer which magnetization is fixed into free layer which magnetization is not fixed and which magnetization direction is used to store the data. The magnetization of free layers is aligned along the injected spin and data is recorded. The first experiment which I did and which was fully successful is a high-speed injection of photoexcited electrons into a nanomagnet. With this experiment, the first challenge a very fast injection of photoexcited electrons into a very tiny nanomagnet with a time interval shorter than 100 picosecond is resolved. The key solution of this challenge was the development of technology of ultra-low resistive iron nanocontact on gallium arsenide. The solution is all about the technology, how to make the resistance between iron nanocontact and gallium arsenide not low, but ultra low. Once more about the importance of fast injection of photoexcited electrons. The number of injected spin-polarized electrons should be sufficient for the magnetization reversal of a nanomagnet. In case of fast injection, all spin-polarized photoexcited electrons are injected into the nanomagnet and data is recorded. In contrast, in case when the spin injection time longer than spin lifetime, the spin information dies before entering the nanomagnet. Its data is not recorded. This is the experimental setup which I used to measure the injection time. The pin gallium arsenide photodetector has iron nanocontact. The beam of 100 femtosecond pulse lasers focus into 4 micrometer spot at the contact, and the photocurrent is measured by a high-speed oscilloscope. This is measured data of this experiment. Measured voltage by the oscilloscope shows the time evolution of photocurrent flowing through the iron nanocontact. The data was measured for identical size iron nanocontact, but which have a different contact resistance. The injection time is substantially depend on contact resistance. And the smallest resistance, shown by green line, the injection time is safely within spin lifetime of 100 picosecond, shown here by yellow square. Even small increase of contact resistance makes the injection time substantially longer. I should mention that in all 3 cases, the contact is ohmic and the contact resistance is order of magnitude smaller than conventional contact resistance used for gallium arsenide lasers and amplifiers. Therefore, an ultra-low contact resistance is required to achieve the required short injection time. It is all because a very small area of nanocontact. The second my experiment on recording is an experiment on the magnetization reversal by spin polarized photocurrent. The target was only partially achieved. The magnetization precession due to injection was achieved, however, the full magnetization reversal has not been demonstrated. The largest achieved precession angle was about 20 degrees. Only when the precession angle is larger than 90 degrees, the magnetization is irreversibly switched. This is experimental setup. A magnetic tunnel junction is used as a nanocontact. It has 2 magnetic layers separated by thin dielectric. The resistance of the tunnel junction depends on mutual magnetization directions of the layers. The beam from 100 femtosecond pulse laser is focused into 4 micrometer spot at the contact. This graph shows experimentally measured contact magnetic resistance under illumination of optical pulses of different intensity. The magnetic resistance is measured as function of externally applied magnetic field. At a larger field, the magnetization of both layers are aligned along the field. The magnetic resistance is smallest and it is independent on optical pulses. At smaller field, the magnetic resistance is larger and substantially depends on optical pulse energy. The resistance becomes larger for higher energy of pulses because the spin polarized electron induces magnetization precession in the free layer. The larger pulse intensity is, the more spin polarized electrons are injected, and the larger magnetization precession angles becomes. As a result, the angle between magnetization of free and pin layer becomes larger, and therefore resistance becomes larger. Even so, the achieved precession angle was large. It was not large enough for reversal magnetization switching. This experiment demonstrates that the recording mechanism is working, but its efficiency is not yet sufficient. Numerical estimations indicate that there is a sufficient number of photoexcited electrons for magnetization reversal. The reason why there is a magnetization precession but there is no magnetization reversal is poor efficiency of the spin injection into a nanomagnet. The efficiency of spin injection into a nanomagnet is poor, despite a very good measured charge injection efficiency. It clearly indicates that the high-speed dynamic of spin is very different from the dynamic of the charge. When the charge always is following the gradient of potential, the spin does not necessarily do that. When voltage is applied to the nanomagnet, the charge always flows into the nanomagnet independently of the size of the nanomagnet. In contrast, the spin may be reflected and not be focused to flow in tiny object. New ideas on how to focus the spin injection into tiny object are required. For example, a removal of the N layer in the photodetector might solve the problem of inefficient spin injection. This slide shows my experimental setup and measurement of injection speed of photoexcited electrons. As I mentioned above, it is important that all photoexcited electrons quickly reach the nanomagnet even from the most distant parts of photodetector, like from these edges. What is the moving speed of the electrons? Maybe it is slow and it is a problem. The measurement is done by the same experimental setup. The timing of injection current is measured for two positions of the laser beam, which are shown by the dark and green lines here. The time delay corresponds to the offset between two lines. From measured delay and known position difference, the injection speed is calculated to be exactly the saturation velocity in gallium arsenide of 75 km per second. When the electron moves faster than saturation velocity, it intensively generates elastic waves and therefore is slowing down. It is similar to an airplane breaking the sonic barrier. Therefore, the saturation speed is considered the fastest speed for the normal current of the electrons in a solid. It means that the achieved injection speed is fastest and is not the problem. This slide explains the advanced fabrication technology used for these experiments. The SEM and optical images are from top view. This is the cross sections. Often, instead of 1, 2 nanomagnets are used as nanocontact in order to achieve a sensitive, balanced detection. The diameter of each iron nanomagnet was as small as 50 nanometers, and the gap between them was about 30 nanometers. An individual cold contact is made to each nanomagnet. Here you can see nanomagnet here. The background surface here is PIN gallium arsenide detector covered by SiO2. The laser beam was focused in 4 micrometer spot at the center. Photocurrent was read by a RF probe, you can see here. So this is cross-section, PN photodetector, iron nanomagnet, SiO2 isolation layer, and a top gold nano contact, which is on top contacted by RF probe. In conclusion, a high-speed charge injection and iron nano contact was achieved within spin lifetime of 100 picosecond. The high-speed spin injection was achieved, but its efficiency still has to be improved. The magnetization precession excited by spin polarized photoelectrons is demonstrated. Magnetization reversal by photoexcited electrons still has to be demonstrated. For this purpose, this year I am developing more efficient resonance mechanism for magnetization reversal. That resonance magnetization reverse mechanism called parametric reversal, and you can find more details about it in my website here. There are 3 mechanisms. Each one can be probably used for the magnetization reversal, but it's just still developing. Also in my website you can find more details about this memory here. So you have many parts here. As for final conclusion, the proposed high-speed optical memory might be one fastest possible memory thanks to the unique high-speed switching feature of the spin. The spin can be switched at an amazingly fast speed of about 2.2 terabit per second, which is limited only by a very short dephasing time of electrons in solid. In order to commercialize this memory, all 3 memory functions, the demultiplexing, the reading, and the recording, should be realized in one single device. There are still some unresolved challenges on the way to achieve this goal. However, I truly believe that this very unique high-speed feature of the spin will be used in future high-speed devices.